Verification, validation, and uncertainty quantification is a field with specialized terminology that can sometimes seem a bit overwhelming. The subtle nuances of these terms are essential for conveying precise information. However, if everyone isn't on the same page, it can quickly lead to confusion. Hi, I'm Josh, and welcome to the VVUQ channel, and today we're going to examine a standard published by the American Society of Mechanical Engineers, or ASME, which tries to put everyone on that same page. ASME VVUQ-01 provides simple definitions for all the key terms you'll come across. Plus, it offers valuable insights into each of these terms, making it easier to navigate the world of VVUQ. On top of all this, the good folks at ASME intentionally made the standard free to encourage you to download it, use it, and share it with your friends. For more information on the ASME committee or to download the standard, check the description below, and sit back, relax, and enjoy as we explore ASME VVUQ-01. In this third video, we're finally going to get to probably some of the fun terminology. We are going to talk about verification and validation. We've entered section 3 of the standard, the verification and validation section, so we're going to talk about empirical data, the referent, verification, including both code and solution verification, validation, and finally validation metric. The first term defined is empirical data. Empirical data is defined as measured behaviors of a physical system with associated uncertainties. Now, there's a specific reason that it says physical system, because empirical data can't be simulated data. It has to be real, it has to be measured. It also has to include your uncertainties. If you just have a value and no uncertainties, that's not good. So the committee really wanted to stress, hey, physical system must include uncertainties. Generally, you might think of this as experimental data, which is absolutely fine. I think most people would call it experimental data. But we didn't want to call it experimental data for a couple reasons. One, there's a lot of things that are empirical that are not necessarily experimental. For example, if you have, say, real world data from a system, let's say you have an airplane and you're getting real data from that and it's streaming, that's good empirical data, but do you really want to call that an experiment? And then there's other things that just we don't like to call experiments. For example, data from people. If you're getting let's say blood pressure data or data from cholesterol or a study, people don't like to be called experiments. So we said, okay, fine, calling it empirical data. I just like to think of this as, hey, it comes from usually experiments and it comes from the real world setting. And it can be, I mean, you have some way to measure it. So I like to think of it as these measurements, but with a little bit of fuzz on them. You need to remember that all measurements are uncertain. They have uncertainties. And so that's pretty much what we wanted to define in terms of defining empirical data. So measurements are uncertain. So again, the measured behaviors of a physical system with associated uncertainties, I like to think of it as a fuzzy ruler. Something real and a little bit fuzzy. So once we define empirical data, we can talk about the term referent. Now, referent is a reference value or set of values against which simulation results or empirical data are compared. This is a newer term for me, and I think for a lot of people, I think some communities might have been very used to it. Usually we think of the true value. So we want to compare, say, simulation results or empirical data to the true value. Hey, are you measuring the right temperature? Are you predicting the right temperature? The problem is that true value is very rarely known. I would even go so far as to say it's almost never known, but there might be a couple edge cases, but it's rarely known. So we have to make assumptions about what that true value is. And the way we do that is we usually define something as, or think of something as a referent. And the way I like to think of a referent as, we believe the difference between the referent and the true value is so small that we just ignore any error, any difference between the two, and we call the referent the true value. The other thing that's important here is that reference in the real world, so if we're talking about, say, physical reference, where we have some data and we say, well, we don't exactly know the temperature, but we're going to call it 0 degrees, like you're sticking a whole bunch of thermocouples in an ice bath, you might say the temperature is 0 degrees Celsius. We call that a referent. We can also make use of mathematical reference, so not just physical ones, but mathematical ones, where a lot of times then we will know the true value. So if you have some partial differential equation, you may know the exact solution. You can use that as that referent. So referent, We think of error as the true value minus R value. I like to highlight the true value in gold. I learned mathematics from a Belarusian physicist who liked to basically say that is the true value. It's known only to God, not to mere mortals. So he would like to highlight it in gold. You don't know that value. And so R value, comes from a prediction from a model, maybe a measurement from an experiment. Maybe we just guessed it. The true value is often unknown, and so you can't really do an equation with an unknown value, so we just kind of get rid of it and write in the referent above. So now we can actually calculate the error. So that's pretty much what the referent is. So a reference value or set of values against which simulation results or empirical data are compared. And basically we usually assume that that referent is the true value, or it's at least close enough that we can assume it's the true value. So now with that defined, we can get into the fun terms. Verification. Verification is defined as the process that establishes the mathematical correctness of the computational model with respect to a referent. This is a very broad term, and the important part here is there are many activities in modeling and simulation that can be considered a verification activity. The ones that I'm familiar with: data verification, input verification, procedural verification, code verification, solution verification. This standard only considers code and solution verification. Those other activities are very important, and there's certainly a verification. Verification's a really broad concept, but we wanted to limit the definition of verification to only include code and solution verification. And so when we kind of created this combined term of just general verification, we were only thinking of those two. So yes, data verification, input verification are important, not really what we're talking about here. And I can't really think of a good way to represent this other than verification is math, or maths if you're from across the pond. So verification, the process that establishes the mathematical correctness of computational model with respect to a referent. We'll go into that in much more detail when we start talking about code verification. Code verification, the process of determining that the mathematical models are correctly implemented in the computer code and identifying errors in the software. We were going to use the word computational model there, but the tricky part with just a computational model is a computational model can exist in the abstract. Again, a computational model is just a mathematical model that you can compute. So it's possible to write a computational model on a whiteboard. And for code verification, we wanted to say, no, we want to actually point to the specific computational model you're using. In other words, you're going to actually have this implemented in a computer code. You're going to code it up somehow. So code verification. It's important to understand this is an error identification process, not an error quantification process. The whole point of code verification is to make sure that you're programming what you intended to program. If you did that, great. If you did not do that, it doesn't mean that, oh, we add an uncertainty. It just means you didn't do it. You don't know what the impact of the results are. You go and you fix it. Basically, we're trying to determine if there are any code bugs. And we often do this by, hey, we know what the results of our computational model should be based on the mathematical model. And so we're going to put that same input into our computer code and see if we get those results. So code verification is really comparing our mathematical model to the computational model. We want to make sure those are about the same model. They're not going to be exactly the same a lot of times because we've had to change some things, but within some scope, they should be pretty similar. Well, how do we do that? Well, it's tricky, but almost all code verifications rely on this basic process. We're going to start with two. We have our mathematical model. We have our computational model. We're going to find some input where we can actually compute a result from a mathematical model, XA. So XA is the input, and we can actually use this in both models. We can compute a result from both models, and then we can actually determine the difference between that result. And this difference is the foundation for code verification. If the mathematical model and the computational model are the same, this error is 0. If it's something other than the same, you got problems. So code verification, the process of determining that the mathematical models are correctly implemented in the computer code and identifying errors in the software. I think one of the challenges I see a lot is people kind of confuse code verification with solution verification. Again, code verification is all about making sure your mathematical model is correct. And so you compare the mathematical model and the computational model. Solution verification is quite a bit different. Solution verification is the process of determining the accuracy of a particular numerical solution relative to an estimate of the exact solution of the computational model. In other words, first, solution verification is an error quantification process. In other words, you're going to have an error due to solution verification. You just have to figure out how much. This is not due to bugs in your code. This is if your code acted 100% perfectly, you coded everything exactly how you meant to, you're still going to have this error. And my favorite way to explain solution verification is this is due to the fact that your computational model doesn't have infinite resources. And a lot of times in mathematics, we kind of assume there's infinite resources. We assume that things are true in the infinitesimal. As I let n go to infinity, I get the exact solution. Well, we can't let n go to infinity. For example, we're not going to have infinite decimal precision. We're going to have single decimal precision, or maybe double. We're not going to have infinitesimal mesh size. Our mesh size will be of some length. We're not going to be able to run an infinite number of iterations. We're going to be able to run some fixed number. Because of that, we need to ensure that those parts of our computational model that are impacted by our computer power don't impact the simulation. We start with the same computational model, and we feed this computational model to two different computers. The first computer, our computer, has some limited computer power. The other computer is God's computer. It has infinite computer power. It has infinite decimal precision, infinitesimal mesh, infinite number of iterations. It can do all this amazing stuff that doesn't really exist. And what we're going to do is see how that computational model behaves in each of those computers. And it's important to stress that we're not changing the model. We're just basically giving it access to more computer power. And we're saying, okay, what is the difference? What is the error between the computational model run on this infinite computer? What is the error and the computational model run on my computer? If that error is too big, then it means that we've probably done something wrong. So in other words, even though you're running your computational model on a computer with some limited resources, the basic idea is that if we give you more computational resources, your models, it might get a little bit more accurate, but it's not going to get a lot more accurate. Your model, even on those finite resources, still does a very good job, especially if you would think of comparing it to that model on the infinite computer. So, solution verification, the process of determining the accuracy of a particular numerical solution, in other words, the numerical solution from your computer, relative to an estimate of the exact solution of the computational model. The exact solution is the model that's run on that infinite computer. We don't have it, that's why we say we need to estimate it. And so this is just that ideal computer versus your computer. With verification defined, we can define validation. Validation is the process of determining the degree to which a model represents the empirical data from the perspective of the context of use. Now, validation is an error quantification process. That's why it says the degree to which. In other words, we want to say not just, oh yes, it's validated and it's not. Please never use that language, but you're trying to say how close your computational model was to predicting some empirical data. And we want to stress the importance of comparing to empirical data. Comparison to other simulations is generally not considered validation. Finally, saying validated is not a good thing. This term, it creeps in, it gives the impression that, oh, now I can use this model at all points in the future and I'm validated and I'm always going to predict exactly what my empirical data says. Not really. Often validation, you can kind of think of it as, hey, I've demonstrated that my model predicts empirical data for some specific use, but you can always generate more evidence. In other words, you can always compare to another data set to show the power of your model. So validation, you have the real world, you're representing that on the computer, and then you're comparing the two. So validation, the process of determining the degree to which a model represents the empirical data from the perspective of the context of use. And it's just that real world data versus how you're modeling that real world. Finally, validation metric. Validation metric is a term that I didn't really like, but we need it. And everybody uses it, but I feel like not a lot of people think of it or even call it a validation metric. It's a mathematical measure that quantifies the level of agreement between simulation results and empirical data for some quantity of interest. In other words, when you're comparing your results to your simulation results to data, however you're doing that comparison, that's your validation metric. And that's really important. So how do you quantify the difference between the empirical data and the model's prediction? You're going to use some validation metric. There's a ton of different ones you can use. First thing you're going to be interested in is this variable you're interested in comparing. So a simulation might have many variables. You have temperatures, you have pressures. So you have to decide, well, which of those am I going to focus on? Am I going to compare the temperature I measured to the temperature my model predicted? Or am I going to compare a pressure I measured to a pressure my model predicted? And then I'm going to consider, well, how am I going to compare those values? Am I going to consider it point-wise? Am I going to compare distributions? There's a bunch of different ways. And I think the important thing with the validation metric is that you can change the validation metric and it will entirely change how much you may trust your computational model. For example, you might have one computational model that does a great job of predicting temperature and an absolute horrible job of predicting pressure. Or it might do a great job of predicting instantaneous temperature, but a horrible job of predicting some pressure as a function of time. And so changing that metric, understanding that metric, it's going to be really important. And it's all going to basically point back to, well, what's your question of interest? What are you trying to answer in the first place? Validation, we talked about how that's comparing the real world to the computational model. And now we need to come up with some way to measure that. So we need to measure the real world, and we need to measure the computational model in the same way, but then we also need to realize that, again, those measurements need to be fuzzy. So it's basically however we consider that comparison, our measurement of the real world, and the difference between that and then some measurement of our computational model. And how you take those measurements and how you do that comparison is all in that validation metric. So validation metric is a mathematical measure that quantifies the level of agreement between simulation results and empirical data for a quantity of interest. I like to think of a function as a mathematical measure and then made the function a little bit blurry to represent, hey, you also have to account for the uncertainties, because that's a major part of the validation metric, to account for uncertainties both in your empirical data and your simulation results. All right, let's recap. We went over section 3 of the ASME VVUQ-01 standard. First, we talked about empirical data, how it's just data you're measuring from the real world, and referent, which is just the value that is the true value or is close enough that you're going to consider it the true value. Then we talked about verification, how we're specifically focused on code verification, making sure the mathematical model has been correctly implemented in the computer code, checking for things like bugs, and solution verification, making sure you're using enough computational power. Your mesh size is small enough, you're using enough iterations, you have enough decimal precision. Then we talked about validation, comparing our computer predictions to real-world data, and the validation metric, that way we're doing the comparison. Remember, you can download the standard using the link in the description. It's freely available, so feel free to take it, use it, share it with your friends. Additionally, I made the PowerPoint presentation available, so feel free to take that, use that, and share that as well. Finally, in the comments below, please let me know what you found wrong and what you thought was useful. Thanks for watching.